Hello, this is Mrs. Mitchner and welcome to Finite Math today. Today we're working on section 3.2 and we'll be finding a maximum or minimum of a objective function. Now look at the box on the page of the notes on 3.2. You'll look up there that says a linear programming problem in two variables x and y consists of maximizing or minimizing an objective function. Now notice that objective function is z is equal to ax plus by, where a and b are given real numbers, not both 0. And if I look there at my example number 1, notice in bold I have z equal to x plus 5y. This is a form that we will put our optimization functions in, and most of the time they will be given to you except in story problems, but we won't have to worry about story problems today. So we look at these inequalities, and these are basically the same type of problem that we've been doing. And remember, this is just to kind of jog your memory, these two last inequalities just means we're going to be graphing in the first quadrant. Okay, so I'm going to label this equation 1, 2, and 3, and I'm going to graph using x and y intercepts. Now, one thing to keep in mind today, if I'm going too fast, all you have to do is have whoever's running the mouse pause me, rewind, whatever. But you can pause, and so everybody can catch up. Okay, here's equation number 1. I think I'll put it right here. And it is x plus 4y is less than or equal to 12. Okay, remember x and y intercept. You put a 0 in for x. It's like covering up the x, and you get 4y equal to 12. So y is going to be 3. Put a 0 in for y, plug, and you just kind of cover up the 4y. That's going to go away. So x is going to be 12. So I have an ordered pair 0, 3. 1, 2, 3. And then I have 12, 0. Okay, now I'm just going to warn you ahead of time. My ruler and my pen don't match up on this fancy little piece of equipment. So if I'm off a little bit, oh, that's not too bad. I'll just adjust a little bit. Okay, so once you get your line graphed, we're going to then pick a point either below or above that line. I always like to pick the point 0, 0. If I plug 0, 0 into my inequality, you have to ask yourself, is that a true or a false statement? Well, is 0 less than or equal to 12? That is true. So I would shade the bottom part. So I'm just going to put a 1 with my little arrows like that. Okay, since I've got different colors here, I'll just use blue. Equation number 2, what is that? X is less than or equal to 8. Now that one I can just go over here to where x is equal to 8. Here it is. And that should just be a vertical line at x equal to 8. Now, like I said, I'm having a little trouble here. Alright, there's equation number 2. And if I want everything less than 8, I'm just going to be shading to the left. Equation number 3, I have x plus y is greater than or equal to 2. Again, x and y intercepts. Plug a 0 in for x, and that means y is going to be 2. Plug a 0 in for y, and that means x is going to be 2. So I have 2 and 2. Then I draw my line. These are all solid lines because they're equal to. And I'm going to pick the point 0, 0 and plug into both x and y in equation number 3, which is in red. Is 0 greater than or equal to 2? That is a false statement. 0, 0 is below my line. This is equation number 3. So I'm going to be graphing above. Okay, so we're looking at the black, the blue, and the red line. I need to go to the left of the blue line, above and to the right of the red line, and below the black line, staying in the first quadrant. So let's get a fun color here. Let's get something like purple. This is the best I can do. You guys can use highlighters if you want. It always makes it a little bit more fun. But there we go. That's the area that we're looking at. And remember, we would also find vertices. Vertices can also be called corner points. and so we need to find those points. Now what I like about graphing using your x and your y intercepts is you can always find those x-axis corner points rather easy. Okay, so I'm going to make a sideways chart, and I'm going to look at, say, this one right here first. That vertex is at 0, 2. So then I'm going to come up and I'm going to put my smiley face so you know where I'm pointing to. Right there, that vertex. Let me just put, that vertex is going to be at 0, 3. So I'll just put smiley faces at all my vertices. I've already done that one. Let's do this one right here on the x-axis. So that would be the ordered pair 2, 0. Now if I go to the next one, down here on the x-axis, that's another vertex. And that, remember, was on my line x equal to 8. So that ordered pair is going to be 8, 0. Okay, now for my last vertex. For my last vertex right there, that's kind of hard to see, but I can I know that x is equal to 8. So I look and see, well, that's intersecting with equation 1. So let's go to equation 1. If I have 8 plus 4y equal to 12, what is y going to be? Well, I subtract 8, so I get 4y equal to 4, so y is going to be 1. So you look and see what two lines are intersecting. In this one, since you knew that you had x equal to 8 as that vertical line, you could get your third or your last vertex or your last corner point by plugging 8 into equation number 1. It's real important that you go through and you label your equations on your graphs because it's kind of hard to figure it out later what equation is which one. Okay, now this second part, what I'm going to do is this is going to be my z. Now z, remember, was equal to x plus 5y. I should have moved my chart down a little bit to the right. So this is, let me just kind of do it like this. That chart right there, that's z equal to x plus 5y. So I'm going through each one of these vertices and plugging in 0 for x and 2 for y into the equation. And then I go to the next one, plugging in 0, 3 into my equation. I'm finding the values for z in each one of these at each one of these ordered pairs. So 0 goes in for x, so 5 times 2 is 10. 0 goes in for x, so I get 5 times 3, which is 15. Plugging in 2 for x and 0 for y, I just get 2. Ordered pair 8, 0 would just be 8. And the ordered pair 8, 1, 8 plus 5 times 1 is 13. Okay, so we want to find the maximum and the minimum, so we just scan that line in red, and let's find the minimum first. So we have a minimum value of 2 at the point 2, 0. We have a maximum value. Well, I'm not writing very neatly today. Let me rewrite that. I have a maximum of, what's the highest number? 15 at the point 0, 3. Okay, when we get into story problems, we'll have to be a little bit more specific, but today we can just kind of talk about the ordered pair. There was example number 1. Wasn't that fun? Okay, let's go to example 2. Example 2, kind of the same thing. I need to maximize the quantity. And let's find a minimum too. I guess I don't have both of them on there. Let's see if we can find a minimum and a maximum both. And here's my z equation. Now remember, we don't graph that. That's just used in our chart. So let me get my graph up here again. Whoops, smiley faces, where'd they come from? This might be the first time you guys got a recorded lesson. I don't know, I can't remember. Hope it's working out for you. Alrighty. First equation, here we go. I'm going to call this, oh, I only have one equation. Well, that's going to be kind of easy. Let's graph it in purple. Equation 1, x plus y is greater than or equal to 1. using my x and my y intercepts. Plug in a 0 in for x, I get 1. Plug in a 0 in for y, I get 1. So if I look at my graph down here, now remember, there's the part right there that's putting it in the first quadrant. If your graph paper does not have axes on it, I guess I didn't address that issue. Here is my y-axis. When I'm doing these problems and I know I'm just using the first quadrant, I will put my axes real low so that the graph being shown is mainly the first quadrant. Here's my y, here's my x. I guess it showed up on mine. I don't know how it's showing up on your notes. I forgot to look. Alrighty, so I'm not going to redraw those in because mine already has it in there and it gets kind of messy if I leave it in there. And I'm going to go to the point 1, 1, 0, 1 I mean, and 1, 0. And this is the only equation I have. But I know I'm staying in the first quadrant. So in the first quadrant, I need to pick out then, do I shade above or below? So I put in the point 0, 0. Is 0 greater than or equal to 1? Well, that is a false statement, and 0 is on this side. Therefore, I have to shade the opposite side. So I'm going to go and stay in the first quadrant. Now, this one, remember, is one we would call unbounded. Don't get too hung up on being neat on shading. So this is unbounded. It's going to go on forever and ever in that direction. Okay, so we just need to shade a little bit like that. When you have an unbounded region, do you still have corner points or vertices? And the answer is yes, you do. So here's my vertices. I've got boom, boom, just those two. I'll make them flowers this time. So if I look at that, here's my little chart that I'm going to do. I'm going to kind of put more space here. Z is equal to x plus 2y. That's what I like to do here, is put the equation there. And these are my corner points or vertices, and they are at 0, 1 and 1, 0. So put those both there. So now I'm going to go back then and plug the points, the vertices, into the z equation. X plus 2 times 0 is just going to be where x is 1. That's just going to be a 1. And 0 plus 2 times 1 is going to be a 2. Now, if I look at this, think about what we have. We don't just look at that and say I have a maximum at 2 and a minimum at 1. That is not what we have. Since I have an unbounded region up there, what we have is we look at this and we say, well, here's our minimum. So I have a minimum of 1 at the point 1, 0. But a maximum does, I don't want to say it does not exist. We don't have a maximum. Maximum, none. I guess it would not exist. Okay, it's just going to go on forever and ever. You're always going to find a bigger point since those x and y values can go to infinity. So we just have a minimum value on this one. Okay, next page. Existence of a solution, you can read that box up there. Fundamental theorem of linear programming. This is what we have been doing, is using this fundamental theorem of linear programming, which states the optimum value for a linear programming problem occurs at a vertex of the region of feasible solutions. Our region of feasible solution is the graphs that we just did. Boom, that one and the one over here. These are our feasible regions, our shaded areas. And so we're just going to be finding the vertices of those shaded regions, and that will be what we plug into our optimization equation, and we can either find the maximum or the minimum. The optimal value, that's a max or a min. Okay, let's do another one here. We're going to minimize this one. Okay. So I have x plus y, make sure I wrote my equations down right. X plus y is greater than or equal to 1. 2x plus 4y is greater than or equal to 3. Yes, and I'm in the first quadrant. Is my z equation x plus 2y? Yep. Okay, so once again, we're going to start by graphing these equations. Forgot to shut the daisies off. They showed up again. Alrighty, so the first equation, I'm going to label this equation 1 and 2. I have x plus y greater than or equal to 1. And you know, if I look at this, I'll be very honest with you. Sometimes I don't start graphing until I find my x and y intercepts for both of them. Put 0 in for x, I get a 1 for y. 0 in for y, I get a 1 for x. So those are very small numbers. Let's go to equation 2. What was equation 2? 2x plus 4y is greater than or equal to 3. So if I look at this, I plug a 0 in for x, I get y to be 3/4. Oh, that's not fun. But we know 3/4 is 0.75, so we can deal with it. And if I put a 0 in for y, I get x to be 3/2. Oh, that's not fun either. But that's only 1.5, so that's not really hard to work with. Okay, so if I look at my numbers, let's think about this. The largest number is 1. The other ones are 0.75 and 1.5. So how about I let each one of these be a quarter of a point? That's what I like about not putting my labels there. So there's 1 and there's 2. And we'll do the same for the x and the y axes. Oh, by the way, you need to put in your x and y axes if they're not on your graph paper. Kind of put them down here lower. You just don't know how weird it is to be sitting here in the classroom talking to nobody and pretending like you're here in the class. But anyway, I'm letting each one of these be equal to a quarter. Okay, I think I am ready to graph. So I'm going to go over here for my first line, and I'm going to graph that one in blue. So I go 0, 1, 1, 0. This makes it much easier to graph here since I rescaled that axis. And then I'm going to, there we go. This is equation number 1. Plug in the point 0, 0. Is 0 greater than or equal to 1? That is false, and 0 is below the line, so I'm going to be graphing above the line. Okay, here's my other equation graphed in red. 0 and then 0.75 is going to be here. And then 1.5, 0 would be right here. Graphing that one. Plugging in the point 0, 0 is 0 greater than or equal to 3 is a false statement. 0, 0 is below the red line, so I'm going to be graphing above the red line. And I am, in fact, keeping in the first quadrant. Don't always assume that. Always look and see. I am keeping in the first quadrant, so once again, I have my unbounded region. There we go. And just keep it in the first quadrant. Just be careful that you do that. Okay, vertices. I'm going to make my vertices stars this time. Now my vertices are the corner points that are touching the shaded area. So I'm going to have that top one right there in the middle and over here. Okay, along the y-axis, let's just start with my chart here. My z equation is, I'm going to make sure I have enough room for that, z equal to x plus 2y. Now that along the y-axis was the ordered pair 0, 1. The star point along the x-axis would be the ordered pair 1.5, comma 0. And then I have that point that's kind of in the middle of nowhere. Now, the last thing I want you to do on these is to guess. So I look at that and I know that it's equations. We don't have a lot of equations here. So I know it's the intersection of equation 1 and 2, and that's why I label these. Whoops, forgot to label it. I have equations 1 and 2 intersecting right there. So I'm going to come down here and I'm going to write my equation 1 and 2 together. X plus y equal to 1 and 2x plus 4y equal to 3. And I'm going to solve those using elimination. Now I like using elimination. You can use substitution if you want, but I'm going to get rid of the x's by multiplying by -2. So I'm going to get a negative 2x minus 2y equal to negative 2, and then a 2x plus 4y equal to 3. Adding those together, the x's cancel, so I get a 2y equal to 1, so y is 1/2. Now, depending on how accurately you graph, does that look like y is 1/2? Well, I was off just a little bit on my graphing. That can be expected on this little machine here, but yeah, it just depends on how thick your pencil lead is, on how accurate you can really be in the placement of that um, ruler. Now you also know that x plus y is equal to 1, so if y is 1/2, x is going, whoops, getting in a hurry here. X is equal to subtract 1/2, x is 1/2. So my other ordered pair would be 1/2, 1/2. So I wanted to do this one with you just for you to realize that yes, you have to accurately find those points of intersection, and don't rely on your graphs because you really never know how accurate your graphing really is. I know you guys are good, but we want to be sure we get the right answers. Okay, so now I'm just going to plug in 0, 1 into the z equation. Plugging that in, I'm going to get a 2 for this one, and I get 1.5 for here. And plugging in 1/2, I'm going to get 1/2 plus 1 to get 1.5. Okay, so looky here. What am I trying to find? First of all, do we have a maximum value? No, we don't, because this one was unbounded. Do we have a minimum value? And that answer is yes. So we have a minimum value of 1.5. And this occurred at two places. It occurred at 3/2, 0, and it occurred at 1/2, 1/2. So there it is. Okay, one more. Now if you want to, feel free to work ahead of me if you want to do this one on your own. If you want to, as a class, if you'd like to just kind of pause me and work this with your study buddy, feel free to do that. I'm just going to go ahead and work the problem. If you just want to do it that way, that's fine with me too. So class, you have your choice. Do it with the study buddy and then check it with me here in a couple minutes, or we can just keep working. So you decide, and here I go. This one. Now what I wanted to point out on this one just says graph the set of inequalities and find the corner points. It does not say anything about finding a maximum or min. There's no z equation. So this is kind of like something that just kind of goes back to section 3.1. But notice, do you see x greater than or equal to 0, or do you see y greater than or equal to 0? And hopefully the answer is no. Okay, so this is not in the first quadrant. So let's just kind of graph this system of inequalities. So I'm going to label this equation 1, equation 2, and equation 3. Now again, I'm going to start getting in the habit of just finding my x and my y intercepts first. So then my pen is not quite working. So then I can see if I need to scale anything. So plugging in for x and y, I plug in 0 for x. Okay, I might have to pause this and see what's going on. My pen's doing funny things. Might be my computer trying to pick up the internet. I don't know. Put a 0 in for x and I get y to be negative 3. Put a 0 in for y, I get x to be 3. So there's that equation 1. We'll graph that one in black. In blue, I have x plus y less, 3y. X plus 3y less than or equal to 3. And so I just do my ordered pairs. 0 for x, I get 3 for y. How about 1? If I plug 0 in for x, I get 3y equal to 3, so therefore y is 1. Plug 0 in for y, I get x to be 3. And equation number 3, I'm going to graph in red. See, I'm really not writing this sloppy. This pen's doing weird things. Okay, so I have 3x plus y is greater than or equal to negative 3. Put a 0 in for x, I get y to be negative 3. Put a 0 in for y, I get x to be negative 1. Okay, so it just looks like I have a lot of 1s and 3s and -1, -3s, and it's not necessarily in the first quadrant. So let me find a graph that's going to work for that. Nope, it's not going to work. Um, Going up to 5, that should work. Yeah, I think that'll work. Okay, so let's graph the black line. 0, -3, and 3, 0. Now again, I'll be able to use my point 0, 0. Here's equation 1. If I plug in 0, 0, I get 0 less than or equal to 3. So I'm going to shade the side that 0, 0 is on, which will be the upper left-hand part. In blue, I have 0, 1, and I have 3, 0. And I graph that one. Kind of missed my point, but that'll be alright. And then I have 0, -3, and I have -1, 0. Oh, that's pretty bad. Try again. Okay, this is equation 3, and this was equation 2. Okay, blue one, I forgot to check. 0, 0, it's true. 0 is less than 3. 0 is below, so I'm going to graph below the blue line. On the red line, put in 0, 0. Is 0 greater than or equal to -3? That is true. So I shade the side that 0, 0 is on of the red line. So of the red line, I'm going to go to the right of that. So once again, just testing the point for each of these lines, the point 0, 0. So I want to shade below the blue line, above the black line, and to the right of the red line. So I think you can visualize that, and we'll just see if I can graph it in this fun color, this area right here. Okay. There's my feasible set. That's my region. And now I need my vertices. My vertices, I think I already have these two because I was graphing them. So I have corner points, sometimes known as vertices, are going to be at 0, -3. I also have 3, 0, and then I have the one I'm not so sure of. The one I'm not so sure of, let's kind of put a smiley face on it, is right there. So I'm looking at that. It's the intersection of equation 2 and equation 3. So let's write down equation 2 and equation 3. Equation 2 is x plus 3y is equal to -3. And equation 3 would be 3x plus y is equal to -3. Do I have the right equations? Equation 2, x plus 3y equal to a positive 3. I was thinking those didn't look right. And then 3x plus y, maybe double check that one. 3x plus y is equal to -3. Okay, now it's looking better. Okay, so we just have to decide what do we want to eliminate. So I'm going to take the top equation and multiply it by -3 to eliminate the x's. So I get a -3x minus 9y equal to -9, and then I have 3x plus y equal to -3. So what I get here will be a -8y equal to -12, so y is -12 over 8. Well, I can't really comprehend that until I reduce it. Y is equal to, see, 4 will go into the top 3 times, 4 goes in the bottom twice. So I get y to be a negative over a negative, Mrs. Mitchner, happens to be a positive. Let's get that straight. And so now I get y to be 1.5. So I need to plug it back in to, which one? Maybe 3x? 3x plus 3 halves is equal to -3. I'm plugging it into this equation right here. So I get 3x equal to negative 3 minus 3 halves. So I'm going to get a common denominator there. So I get 3x equal to negative 6 over 2 minus 3 over 2 would be negative 9 halves. So I get 3x equal to negative 9 halves. And then I need to get rid of the 3, so I'm going to multiply both sides by 1/3. So I get 1/3 times 3x equal to negative 9 times negative 9 halves times 1/3. 3's cancel. So I get here x equal to, this will reduce here to a negative 3 over 2. So x I get to be negative 3 halves. Wow. Here's my last vertex. X was negative 3 halves, y was 3 halves. Well, there we go. I didn't want to go longer than a half hour, and I'm almost at 31 minutes. And I hope you got it. And if you have some more questions, feel free to come in and see me during SRT tomorrow. And you have the rest of the period to work on getting this homework done. Help each other out, and feel free to ask the sub any questions. And I will see you on next class period. Have a good day, and hope you enjoyed your recorded lesson.